Hello all, myself Sambasiva Rao, working as Assistant Professor in the Department of Civil Engineering at VIGNANA VJYT. So I welcome you all to the lecture series on payment materials, and the topic of discussion for today will be Marshall method of mixed design. So you might be familiar by now what is a mixed design for concrete. So similarly we are going to have one mixed design for asphalt mixtures, so which is called as Marshall method of mixed design, and the name of the mixed design is named against the scientist who is nothing but Marshall. So if you look at the different layers which are present on the cross section of a flexible pavement, this is a surface layer which is also called as wearing course. Next one is binder course, which is again of bituminous in nature, and followed by these two are base course and sub base courses, and followed by subgrade. So I'm not going to explain the details of what is the purpose of each and every layer over here. So our discussion will be restricted only to the Marshall method of mixed design over here. So you can see here there is a surface course. Again, these two layers are said to be bituminous layers, or BT layers, are also called as bound-led layers. So because we are having a binder over here, which is nothing but the bitumen, so these layers are said to be bounded layers, which means nothing but they will be having intact holding themselves. So that is why it is nothing but bounded layers. And again, base course and sub base courses, these are said to be granular layers. These are nothing but granular layers or unbounded layers. These are also called as unbounded layers. And then you are going to have a subgrade, followed by in the bottom you are going to have a embankment. So now we have a discussion because this is a bituminous mixer. So Marshall method of mixed design is only applicable for these two, which is nothing but bituminous layers or bounded layers. And you can see here there is three different coats which are present over here. One is nothing but the prime coat, next one is tag coat, and next one is seal coat. We are going from top to bottom or bottom to top. When you come from top to bottom, it is STP. So the prime coat is very important. It is provided between the unbound layers and bound layers. So I repeat here, there is a sub-base course over here, which is an unbound layer at the granular layer, and in the top you are going to have a first bituminous layer, which is nothing but the binder course. So this is the layer. So there won't be enough amount of contact between the bound layer and unbound layer. So as a result of that, we are going to spray some amount of bitumen emulsion on the top of the unbound layer, which is nothing but the sub-base course. Base course, in order to have a contact, in order to have a better contact with the coming binder course. So that is why it is said to be the prime coat. So that is the purpose of the prime coat. And next one is tag coat, is nothing but when you want to have a better contact or better adhesion between bituminous layers, either it might be one is nothing but binder course and the surface course, then you are going to provide the tag coat. So that is nothing but they are put in tag between the bituminous layers, and the surface layer and the top layer or the top coat which is going to provide on the surface layer is nothing but the seal coat. We are going to seal all the voids which are present in the surface course, which is nothing but the wearing course over here, BC, bituminous concrete. So this is the figure which I have taken from the IRC 37, which is nothing but code book for the design of flexible pavements. So there is a dual wheel assembly over here, and this is again bituminous layers. Just now we have discussed this. So the top layer might be bituminous concrete and the bottom layer might be dense bituminous concrete. Both of them put together, we call it as bounded layers. And again, these two are nothing but unbounded layers. One is nothing but granular base, and next one is granular sub base, which might be at the treated condition or untreated condition. And next one is we are going to have subgrade. Below that, we are going to have an embankment. So this is also a very important question which has been asked in competitive examination number of times. So what are the critical locations for finding out the fatigue and rutting in a flexible pavement? So the critical location to assess is nothing but the bottom of the bituminous layer. So this is the bituminous layer, which is nothing but BC plus DBM combined. So this is the bituminous layer, but that too horizontal tensile strain. Here they have written it as tensile strain, but it is nothing but, to be very specifically, it is nothing but horizontal tensile strain. So the strain should be in tensile in nature, and that too horizontal tensile strain. So this is an indication of the fatigue of the what is happened in the bituminous layer. And next one is fatigue distress. So at the same time, you are also another critical location is nothing but the vertical compressive strain. So this is an indication of rutting failure in the pavement. So if you want to assess the rutting in a pavement, you have to assess the what is a vertical compressive strain. So this is nothing but, in the previous it is nothing but horizontal, and this is nothing but tensile strain. So horizontal, this is the horizontal direction, and that to tensile, so which are pulling out each other. And in this condition, you are finding on the top of the subgrade, which is nothing but the vertical in nature and that to compressive in nature. I repeat, the two critical locations which are necessary for carrying out the stresses is nothing but, for carrying out the distresses is nothing but, one is nothing but the for fatigue it is nothing but the horizontal tensile strain at the bottom of the bituminous layer, and the other one is nothing but for rutting condition it is nothing but vertical compressive strain on the top of the subgrade. So you can remember like this, it is on the top of the bottom layer. So this is the top of the bottom layer. So this is the bottom layer on the top of this, and this is nothing but the top layer, and this is nothing but bottom. So top of the bottom layer and the bottom of the top layer. So these are the two critical locations, very important. So next one, so this is what we are seeing, a loose bituminous mixture over here. So how this has been attained, we are going to see in few slides. So this is nothing but some aggregate, and we are going to add some amount of binder to this such that it will look like this, and the same amount of bituminous loose mixture, bituminous asphalt mixture is brought into the site, and it is transported to the site, and it is subjected to paving condition, and it is being rolled like this such that you will have a finished surface which is nothing but the top surface bituminous concrete. Now we are going to see how this bituminous concrete is going to perform or in the field conditions. So before that you have to do the test, and you have to give some design, that is nothing but mixer design, and you have to generate a job mix formula. So for which we have to conduct a test, or for which you have to prepare a mixture in the laboratory conditions. So you have to take the mineral aggregate of the different gradations or different sizes. So this is you can see the mineral aggregate, and then you see there is some amount of bitumen being added over here, and then you have to mix that till a uniform coating is being applied on the surface of the mineral aggregate, and then you have to compact the sample such that it reflects the compaction under the field conditions, and you can see a Marshall specimen of this nature. So this is one automatic mixture which is available. So you can either go for manual mixing, or you can go for automatic mixing also. So here you have to take the whatever it is, either whatever the condition it is, you have to take the required amount of mineral aggregate, and you have to keep in aside the amount of the bitumen what is required. You have to go ahead with the calculations priorly, and then you have to go for mixing like this in this condition, and after that the entire mix is need to be compacted. So there is a Marshall mold over here. So this is nothing but the bottom one is nothing but the Marshall mold, and next one this is nothing but a collar mold, and this is a base plate. Okay, so I have got a sample of this Marshall mold. So you can see this. So this is the Marshall mold which is in the bottom side. So this is the Marshall mold which is, we are going to have a groove on the top side and the bottom side. So initially the entire aggregate, the amount of the aggregate what we generally take for conducting this Marshall method of mixed design is nothing but 1200 grams of mineral aggregate. So the mineral aggregate alone will be 1200 grams, and after that you are going to add some amount of bitumen. So after compaction, that entire bituminous mixture of compacted specimen will be within inside this layer. But when it is a loose mixture, this material will be overspilling outside. So because of which we want to provide a collar mold. So this is a collar mold which is going to have a groove only on one side. So this is nothing but you have to first you have to take a base plate. That base plate will be provided in this condition. So there is a base plate over here. So at this condition, so that will be provided in the Marshall compactor machine. So there will be a compactor machine, and I am taking the setup which is present over here. So I am explaining only this part. So that zoomed condition is this thing. So you will be having a base plate. So this is the base plate which I am having over here, and then I am having a Marshall mold. So you have to keep the Marshall mold like this condition, and then you have to keep on the top of that you have to keep the collar mold. So you keep the collar mold, and you keep the aggregate whatever it is. So the loose asphalt mixture whatever you are prepared by adding mineral aggregate along with the bitumen after heating. So here again the heating conditions are you have to make note of the heating conditions. The aggregate has to be heated minimum to a temperature of somewhere around 150 to 160 degrees centigrade, and then you have to heat the bitumen according to your mixing and compaction temperatures of the bitumen. So that you have to refer to the code. So as the discussion is only at the level of UG level, so I'm not going to discuss the mixing and compaction temperatures. So you take whatever the bitumen of your interest, and you add the bitumen according to heating conditions. So you heat both of them priorly, and you add both of them, and that should be mixing again, that should be mixed for a period of time such that it attains some amount of temperatures, and then that loose mixture has to be transferred into this after fixing into the this automatic compactor of the Marshall mold. So that is how you are going to get this. So you are going to put the loose mix, so it will be coming up to this location, and after then there will be automatic compactor. So there will be a Marshall hammer over here. So this is again the height of this fall will be 457 mm. So and the weight of this hammer will be 4.5 kg. So this will be actually, this is in pounds, which is nothing but 10 pounds, and this is nothing but 18 inches. So the hammer will be falling from the top of this. So you have to lift this hammer up to this height and release this hammer. So you can go for either again manual compaction or automatic compaction. So either ways, so you have to do it compaction. 75 number of blows is required. So and after that, once you have subjected this compaction for one side, then you have to rotate this specimen or Marshall mold in the reverse direction, and you have to keep this again collar mold on the top of that, and you have to give compaction on the other side also. Okay, so that is what it is required while going for compaction on the Marshall mold. So compaction is necessary for both sides. And I have taken an example for bituminous concrete, which is nothing but the surface course of gradation 1. So I am taking this gradation. We have gradation 1 and gradation 2. This is the BC1, this is the BC2. So and the sizes are nothing but, you can have the sieve size which are passing from 50 to 65 mm, and this is 30 to 45 mm. So so these are the different sieve sizes what is required for bituminous concrete 1 BC1. So you can see here the entire amount of aggregate should pass through 26.5 mm sieve, which means nothing but, this is nothing but 100% passing. And after that, here only 79 to 100% will be passing. Why? Because there will be some amount of metal retained on this particular sieve 19 mm. Similarly, these are the percentage, cumulative percentage passing. So 100% of the metal will be passing through the 26.5 mm sieve, and some part of the metal will be retained on the 19 mm sieve. As a result, only the percentage of passing will be 79 to 100. And if you look at the BC2, 100% of the metal will be passing through 19 mm. So it means nothing but BC2 is somewhat smaller gradation bituminous concrete when compared to that of BC1 gradation. So and this is bituminous bitumen content 5 to 6%. I will explain this in the next slide. So this you can see here, I have taken the BC1 which is of the shown in the previous slide, 26.5 mm, which is nothing but the lower limit, upper limit is 100%, and 19 mm sieve, it is nothing but 79 to 100. I have separated it, lower limit, upper limit, and then the same thing has been done for all the sieves. And after that, I have located the midpoint of each and every sieve size. So this is what the actually midpoint. You can go for the midpoint, but midpoint gradation will lead to a dense mix where you don't have required or sufficient number of sufficient quantity of air voids in the field for secondary compaction. So we have to take our job mix formula such that it deviates from the midpoint. So that is what you have to take your job mix formula, just deviating from the midpoint. At the same time, it is between the lower limit and the upper limit. So this, I have taken the job mix formula as 100%, and this is somewhere around 79 to 100. I have taken it as 95, and this is 70, this is 63, and this is 46. So here 95 is higher than this. So till up to this condition, so on the higher side of the midpoint. So you can see here, from here to here, I am the upper side of the midpoint. So 100, 95 is higher than 89.5, 70 is higher than that of 69, and 46 is higher than. And after that, I have deviated little bit from the midpoint toward the lower side. So that you can see in the next graph. And after that, so this is job mix formula, which is nothing but 100% of metal is passing through 26.5 mm sieve, 95% of metal is passing through this 19 mm sieve. Similarly, you have to calculate what is the percentage of metal passing through, cumulative percentage of metal passing through each and every sieve. So this is the job mix formula which I have taken as of now. The sieve gradation what I have taken, you cannot call it as job mix formula until unless you give it finalized mix. And this is weight retained. So weight retained is nothing but 100 minus cumulative percentage passing. So 100 minus 100, it is nothing but 0. 100 minus 95, it is 5%. So this is very, very important. So we are ultimately looking for, even the gradation is given in terms of the cumulative percentage passing, but we have to bring down to the level of percentage weight retained on each and every sieve, not cumulative percentage weight. It is only percentage weight retained. So 5% is retained on overall, 5% weight is metal is retained on 19 mm sieve, 25% is retained on 13.2 cm. So that is what you will get the percentage weight retained. And as I told you that this Marshall mold which I have shown you previously, which is nothing but 100 mm dia and 63 mm height, 63.5 mm height. So like this. So this will be having 100 mm dia. Okay, and this will be 63 mm height. So in this condition, for this metal, for this Marshall mold, a metal of 1200 grams is sufficient. So that metal, in order to get 1200 grams of mineral aggregate, not along with the bitumen, so you have to take 0% means this is 0. 5% of 1200 grams is 60%. Like that, you have to distribute this entire aggregate in different sieves. So in order to get the 1200 grams, this is the corresponding weights that you are supposed to take over here. Okay, and this is the graph that is corresponding to the gradation what I have selected. So this is the upper limit which is represented over here. So where I cannot exceed my job mix formula or the gradation what I have selected. Not it should not be deviate. It should not be higher on this, and at the same time it should not go below this. So there is again midpoint gradation over here, just like I have shown you previously. And this is what the job mix formula, which is in green color. So that is the job mix formula which I have taken. I have told you that my job mix formula is somewhat higher on the higher side of the midpoint gradation till some point of time, and after that it is somewhat lower when compared to that of midpoint gradation over here. So you can see that there is no deviation between upper limit and lower limit. So this you have to plot against the semilog graph. So this is the sieve size and this is the cumulative percentage passing. So this is 100% is passing up to here, there is 100% is passing, and this is how you get the graph over here. And after that you have taken 1200 grams of 1200 grams of aggregate. So I am going to explain some small calculations over here. So 1200 grams of aggregate alone, mineral aggregate. So 1200 grams of mineral aggregate. Okay, so then you have to take the bitumen content. As you have seen the second slide, which is nothing bituminous concrete, we are going to have 5 to 6% as the bitumen content. So this 5% or 6% bitumen content will not be with respect to the weight of the aggregate. You have to understand this means. So if I take 5% of the weight of the aggregate, so 12 5s are, it is nothing but 60 grams is the weight of the bitumen. But in generally asphalt mixtures will be calculated with respect to the bitumen content by weight of total mix. By weight of total mix. I repeat that if you take 60 grams whatever it is present over here, so this will be 5% by weight of the aggregate, by weight of the mineral aggregate. But what I have written over here, bitumen content is nothing but weight of the bitumen with respect to the total mix, by weight of the total mix. So therefore we don't know what is the amount of bitumen that need to be added for a 5% bitumen content by weight of total mix. So we don't know the weight of the bitumen, let it be x, and divided by, so 1200 grams plus you are going to get the same x weight. So this is the weight of the bitumen, this is the weight of the bitumen, this is nothing but the total weight. So this is what bitumen content by weight of the total mix. So I repeat, so if we take an x divided by 1200, which is equal to 5% or 4%. So if I take this as 5%, so then I'm going to get 60 grams. But if I take the 60 grams, so 60 divided by 1200 plus 60, it will not be 5%. It will be less when you go for bitumen. When you go for bitumen content by weight of the total mix. So as a result of that, you have to do your calculations with respect to, I'll explain this with respect to bitumen content by weight of the total mix. So my I don't know the weight of the bitumen initially, so I will take it as x grams, and the bottom is nothing but 1200 grams is mineral aggregate, and the same weight of the bitumen will be carried to the denominator. So this should be percentage of 5%, so it should be nothing but 0.05. So therefore x is equal to 1200 into 5%, which is nothing but 60 grams plus 0.05 x. So therefore x, if I bring over here, so there is nothing but 0.95, x is equal to 60. So therefore x is equal to somewhere around 63 point, you will be getting 63 point something 1 or 2 grams. So this is what in generally if you take the 60 grams weight of the bitumen, that will not be 5% by weight of the total mix. It will be less than 5%. It will be only 5% by weight of the aggregate or mineral aggregate. So this is how you have to calculate the weight of the bitumen that is required. So and then after that you calculate this again the first and foremost step in Marshall method of mixed design is nothing but calculation of OBC, optimum binder content. We don't know what is the optimum binder content, so for which we have to go for trial asphalt content. So the aggregate weight being keeping constant as 12 grams, so you have to start with somewhere around 4.5, or sometimes you can start with 4%, 5% and 6%, because already it has been given in the percentage weight of the bitumen is nothing but 5 to 6. You can start with 4.5, 5, 5.5, 6 or 6.5 like that. So generally assume that you have started from 4%, 5% and 6%. So you have to take the bitumen contents by weight of the total mix as 4%, 5% and 6%, and you have to catch the Marshall specimens. So you have to prepare the Marshall mix, and you have to go for compaction, and you have to get the Marshall specimens of 100 mm dia and 63 mm 63.5 height. And after that you are supposed to conduct some tests in order to get some properties. So and after that you are required to calculate the optimum binder content. So if there is some way where I can separate this is an aggregate volume, this is an aggregate, and this is a bitumen present over here, and this is a percent air voids present in the mix. So as you can see this, So there is a asphalt specimen over here. Generally, we cannot separate the aggregate volume, bitumen volume and air volume. Let us assume that if we can separate somehow all these things separately. So this volume, whatever it is present over here. So I'm keeping this aggregate volume, this aggregate volume, this aggregate volume, this aggregate, and all of them put together aggregate volume, bulk of the aggregate volume as this thing. Okay, and I've removed all of the bitumen over here, and I kept this. This is the bitumen present over here, and this is the air words which are present over here. I'm just separating. This is also called as three-phase diagram. This is also called as three-phase diagram, because we are having three phases. One is nothing but air, interaction between air, binder and aggregate stone. So that is why it is called as three-phase diagram. In order to understand what is the contribution of air, what is the amount of air voids present over here, what is the amount of bitumen, volume of the bitumen. Even though we are very sure what is the amount of bitumen we have added in terms of the weight, but we don't know what is the volume of the bitumen that has been present in the specimen. So at the same time, what is the volume of the stone? So this all put together, we'll get to know what is the volume of the total mix. So there are some equations which are necessary to find out some volumetric properties. One is nothing but volume of air voids, which is nothing but VV divided by VT, volume of air voids divided by volume of the total mix. This can be easily calculated by the formula GMM minus GMB divided by GMM, where GMM is nothing but maximum specific gravity of the mix. Maximum specific gravity of mix. Here M stands for, the first M stands for mix, and B stands for bulk. If it is in bulk, so this is nothing but specific gravity, this is bulk specific gravity of the mix. Bulk specific gravity of the mix. That is the difference between GMB and GMM. So I'm repeating this. GMM is nothing but theoretical specific gravity of the mix, so which is the maximum value, and this GMB is nothing but bulk specific gravity of the mix. This bulk is nothing but, as we all know, that we have just taken Marshall sample, which is nothing but of this, which is nothing but 100 mm dia and 63.5 mm height. So you know the weight of this. Once you remove this specimen, once you extract this sample from the collar, from the Marshall mode, you take the weight of this specimen, you will get the weight. Okay, and then you know the volume. So in order to get the volume, so you can go with two different ways. One is nothing but calculating the saturated surface dry weight and weight in air divided by, like that, just like what we have done for specific gravity of the aggregate. So the easy way what you can do is nothing but what is the volume of this specimen. So you calculate what is the average diameter at three locations using vernier calipers, and then find out this diameter is anyhow fixed, which is nothing but 100 mm dia. So then you calculate the weight, you are going to get some amount of specific gravity. So this specific gravity is nothing but bulk specific gravity. In this, you are going to have some air voids over here. So that is why we are going to have some amount of lesser value, because the volume here already we have understood that there will be some amount of air voids which are present inside the mix. So that is what that will lead to the reduction of the specific gravity, and that is called as bulk specific gravity, because we are taking the bulk of the sample, not only mixture alone. But whereas GMM is nothing but theoretical specific gravity. This you have to do in a pycnometer or asphalt mixture density meter will be there. I am not going to in deep regarding the test how to conduct the GMM or how to calculate the theoretical specific gravity, but just assuming that it is just like you conduct the specific gravity and loose aggregate. So you take the aggregate, you fill into the pycnometer to 1/3 level, and you add the water, and then you go for calculations. That will gives rise to, just like the definition of specific gravity, weight in air divided by weight in water, weight in air minus weight in water. So if you do that, you are going to get this your weight is nothing going to be changed over here, but this volume is nothing but only the volume of the mixture alone, excluding the volume of the air voids. So then this volume will be volume of mix alone, aggregate loose mix. So to be specific it will be loose mix. So the volume of the loose mix. So therefore, as the volume of the loose mix, here it is more because it is present along with the air voids. Here it is less. So therefore, we are going to have GMM a bit higher value, because the denominator being lower, we are going to get a higher value of GMM. So that is nothing but maximum specific gravity or theoretical specific gravity of the mix. GMM stands for mix. I repeat that GMM is nothing but the theoretical specific gravity of the loose mixture. So excluding the volume of the air voids. So weight of the loose mixture divided by volume of the loose mixture, which can be obtained only by doing some calculations. But whereas GMB is nothing but the weight of the mixture, which is nothing but the weight is constant in both GMM and GMB, but the volume is going to be different here. The volume is nothing but bulk volume. Either again you can do that in a different process also by taking the saturated surface dry weight minus weight in air divided by weight in saturated surface dry weight minus weight in water. That you also can do in order to get the GMB. So this is how you get the volume of air voids. So there is another parameter which is nothing but the volume of the bitumen, which is VB, which is denoted by the symbol PB, percentage of bitumen. So already we know that what is the percentage of bitumen that has been considered while casting the specimen, multiplied by GMB. Already you know what is, just now we have calculated GMB over here, and this is GB. GB is nothing but specific gravity of the bitumen. From that you are going to get the what is the volume of the bitumen over here. So you are going to get the what is the volume of the bitumen. We already got what is VA, and this both put together, VA plus VMA. We have just calculated what is VA with respect to GMB and GMM, and then we have just calculated VB, which is percentage of bitumen multiplied by GMB divided by GB, specific gravity of the bitumen. We have got VB also. So this both put together is nothing but volume of voids. So what is initially, if you can remove this air voids and aggregate, so that is the space that are being available. So if we don't have binder, so this entire thing is nothing but void, that is completely void. We have taken this as a single aggregate particle. This is the void that has been created. And then if you want to get the value of VMA, this is VA plus VB. Again, there are different ways of calculating VMA if you go in much deeper manner. So you have to go for the calculation of effective specific gravity of the aggregate, and that has to be incorporated over here. So at the UG level, we are not going much deeper over here. So just easily we are going to calculate what is the volume of air voids and volume of the bitumen. So once you get this V and VB, you add both of them, you'll get VMA. And here it is nothing but VFB, or this is also called as VFB. VMA, VFA or VFB, which is nothing but voids filled with asphalt or voids filled with bitumen. Either of the ways it is same. Voids filled with asphalt is nothing but bitumen. So voids filled with bitumen, VFB is equal to, or VFA is equal to VB. Among the amount of the voids what we are having, the amount of voids what I am having here is nothing but VMA, voids in mineral aggregate. Out of that, how much portion is being occupied by the bitumen? So that is what voids filled with the bitumen. So this you are going to get some value. So this is how you have to calculate the volumetric properties. These volumetric properties are very important for competitive point of view. There have been number of times where there have been questions been asked on this. Very easy. You have to just substitute the values. Majority of the times people skip this topic and will not concentrate much on this. But this is an easy topic where you can get marks easily. So here there are small numericals present over here. So we'll see one after the other. So here the bulk specific gravity already which is there, which is nothing but GMB, is given as 2.33, and next one GT, which is also called as GMM, theoretical specific gravity. Here in this case it is nothing but 2.43, and the percentage bitumen in the mix is nothing but 4%. So that is nothing but 4%. PB is nothing but 4% is the weight of the bitumen. So we have to calculate the volumetric properties. VA is equal to GMM minus GMB divided by GMM. So which is nothing but 2.43 minus 2.33 divided by 2.43. Then you are going to get the percentage of air voids as 4.11%. Similarly, we have to calculate what is VB, voids filled with bitumen. Sorry, percentage of bitumen, VB, volume of bitumen. So here you have to take this as PB, percentage of bitumen, multiplied by GMB divided by GB. Here the specific gravity of the bitumen is also very important, which is nothing but generally very close to water, which is nothing but 1. And here it is 4%, percentage of bitumen multiplied by GMB is nothing but 2.33%, and GB being 1. So you are going to get the value of 9.32 percentage as a volume. Volume of the bitumen. So then you have to calculate what is VMA, which is very easy, which is nothing but the combination of VA plus VB, which is nothing but in this condition it is 13.43%. So among the 100% whatever you have taken over here, among the 100% what you are taken here, 13.43% is initially the air voids what you are having. The rest of that is nothing but aggregate stone. So again there is a limit for which you have to see if you go in deep, what is the minimum percentage of air voids or percentage voids in mineral aggregate should be left over, like that. So, but I am not going into the deep. So 13.43% is left over. Okay, and after that out of this 9.32% is for bitumen, and there is 4% reasonably amount of air voids is present, so which is available for secondary compaction. So this is with voids in mineral aggregate, and voids filled with the bitumen, so which is nothing but VB divided by VMA. So therefore which is nothing but 9.32 divided by 13.43%. So you are going to get 69.3%. So out of this entire voids which are having, which is nothing but voids in mineral aggregate, in the entire voids 69.3, very close to 70% is being occupied by bitumen. So that is what the inference over here you have to understand. So they have given two values, which is nothing but GMB, and next one is GMM. Along with that, they have given percentage of bitumen, and the specific gravity of the bitumen is also given. So I've just substituted in the small formulas, which is nothing but VA, GMM minus GMB divided by GMM, and followed by VB, and followed by VMA, which is nothing but addition of both VA and VB, and VFB, which is nothing but VB divided by VMA. Sometimes this is another question. Question number 2. A bituminous mixture contains 60% is coarse aggregate, 35% is fine aggregate, and 5% is 5% is asphalt by weight. Okay. In this condition, you have to calculate GMM. So that is what they are asking. Determine the unit weight of the mixture with specific gravities. So here in this condition, if they are given specific gravities individually, it is nothing but they are asking us to calculate the theoretical specific gravity. So theoretical specific gravity can also be calculated with these values what have been given over here. So the formula for calculation of specific gravity GMM is nothing but 100% divided by weight of the fraction 1, percentage weight fraction of 1 divided by specific gravity of fraction 1 divided by percentage weight of the fraction 2 divided by specific gravity of fraction 2 plus weight of the fraction 3 divided by specific gravity of fraction 3 if you have percentages. Or else if you have the weights alone, so then you have to take the capital W, which is nothing but all the capital W divided by the weight, not weight proportion. So weight W1 divided by G1 plus W2 divided by G2 plus W3 divided by G3 plus W4 divided by G4. For example, if it is 5,000 grams, so then you add this one to be, that should be equivalent to 5,000. So somewhere around some 2,000 grams over here, 2,000 grams over here, 500 grams over here, or 900 grams over here, or 100 grams over here, and then individual specific gravities. When you are known, be familiar with the weights, you have to take the weights. So this weight over here in the numerator should be equivalent to the individual weights over here. Or else if you are given with 100%, so this percentage should be equivalent to the percentage of this. So that is the easy calculation. So here the problem is being given in percentage, so we'll work out in terms of percentage itself. So here I have given with three proportions. One is nothing but coarse aggregate, and next one is fine aggregate, and next one is bitumen. So first you check whether all of them put together is become 100% or not. So for example, it is 60, 35, 95 plus 5, 100%. Sometimes they'll give this as 60 and this is 40, this is 35, and they don't mention this percentage of the asphalt. But you have to understand indirectly that 60 plus 35 is only 95. So they have left 5% space for bitumen. That is what you have to understand from the given question. Very, very important. So in this condition, it is again percentage. So I'm going to take the percentage of this. So weight percentage of W1 is nothing but 60% divided by specific gravity of coarse aggregate is 2.7 plus the weight percentage of fine aggregate is 35% divided by 2.66 plus the weight percentage of the bitumen is nothing but 5% divided by specific gravity being 1. So you have to calculate this value, which you are going to get the GMM value 2.48 as the GMM value. So this is what you are going to get the GMM value. Very simple, easy. Next one, you are also going to look at the third question. So here the same question I have extended the question to, where I have got the question as GMM as 2.48. So the same question, GMM is already given from the previous question, which is nothing but 2.48%. So this is not percentage, 2.48. So here also it is not a percentage value. So this is GMM is already given. Next one, you have to calculate GMB. So for that, they have given that determine the unit weight of the mixture with specific gravity is already given, the volume and the weight of the Marshall specimen. So just like previously we have seen that the weight and the volume. So instead of taking 1200 grams, the entire weight of the mixture for them, it has only 1100 grams. For us, if you have taken 1200 grams, and if it is 5%, then we came to know that it is 63 grams. So the entire mixture should be 1263 grams. But whereas for somehow they have casted the specimen with a less weight, which is having only weight of 1100 grams as the bulk weight of the Marshall specimen. So in this condition, so therefore you have to calculate GMB, which is nothing but the weight by volume. Weight is nothing but 1100 grams divided by volume is only 475 cc. That is nothing but centimeter cube. So therefore again we have turned out to be GMB value as 2.31. So as you all know that always this GMM value should be higher than that of GMB. Once you are familiar with this, again you have to proceed with the VA percentage, which is nothing but GMM minus GMB divided by GMM into 100. And again you know what is VB. VB is nothing but percentage of bitumen, which is already given as 5%, into multiplied by GMB. You already know that it is 2.31%, divided by GB. If already given that to be 1%. specific gravity as 1. So then you will get the what is VB, and then proceed for VMA, which is nothing but VA plus VB, and then after that you get you have to calculate voids filled with bitumen, which is nothing but VB divided by VMA. So therefore somehow you get the different values over here. So that is the end of the discussion over here. So, and this discussion we'll see in the next classes where you have to catch the specimens with a different percentage. Like I have told you, this discussion what we have done so far is only for single percentage bitumen content. As I told you, that trial asphalt content should be conducted for 3 to 4 percentage trial asphalt contents, and there should be, you have to plot these graphs. So corresponding to 4 percentage, 5 percentage, 6 percentage, you have to conduct again 3 replicates for each percentage. So 3 over here, 3 over here, 3 over here, and then you have to get the graphs. So this is air voids. Just now we have calculated VA. So this is nothing but VA. Once you have different percentage, you get the different volume air voids, and you will get the graph like this. And then this is the density, which is nothing but this is GMB. Here it is nothing but bulk density means GMB, and this is Marshall flow. This is this test we will be discussing in the further classes, where you have to conduct the specimen, where you have to conduct the Marshall test. So where which you will get the Marshall stability, and then you are going to get the Marshall flow. So this graph and this graph will be after conducting the Marshall test, you will come to know. And VFA, just now we have calculated VFA, and this is VFB, voids filled with bitumen or voids filled with asphalt. So these graphs are already 1, 2, 3, 4. These 4 graphs are already known to us. These 2 and these 2. These 2 are supposed to be conducted, and after getting that, we are very much interested to calculate the what is the optimum binder content. Optimum binder content is corresponding to the density, whatever the bitumen content which is having higher density. For example, let it be so for the corresponding to higher density or peak density, this is the bitumen content. So let this be bitumen content 1. Okay, and next one, what is corresponding to Marshall stability? So what is the bitumen content corresponding to the peak Marshall stability? So let this be the bitumen content B2. And another third parameter which is very important, what is the bitumen content corresponding to 4 percentage air voids? So sorry, 4 percentage air voids. So this is the 4 percentage air voids. So I have to extend this line in order to see where is this line intersecting over here. So this is the corresponding 4 percentage air voids, and this bitumen content which I required is B3. So you have to take B1, B2, B3, and you have to take the average value. So B1 plus B2 plus B3 divided by 3. So that you are going to get it, the average OBC, and with that OBC, actually that is a final OBC, optimum binder content, that is the original OBC. Then you have to catch the specimens with this particular binder content, which we are going to get after this calculation, and then you have to proceed for again testing of Marshall stability, whether it is fulfilling the required criteria or not. So that is the end of discussion on Marshall method of mixed design. So I sincerely acknowledge the use of publicly available resources that supported and enhanced the visual clarity of this presentation. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.